All right, welcome to the Crazy Head Chemist. And here we go again with the second part of the solutions video. So this is part number 2 of solutions video. So let's get moving on this one problem right here. Number 16. We have a number of problems yet to complete. 16, 17, 18, and 19. That's 1, 2, 3, 4 and 5 problems. 4 problems here. 16, 17, 18, and 19, 4 problems. Okay, so here we go. It says for this problem, number 16, what is the boiling point of a solution containing 10.25 grams of barium phosphate in 50 grams of water? And we got the constant for the boiling point. All right, so let's see what we can do with this here. So the equation for the boiling point is a boiling point is equal to the normal boiling point plus the change in temperature of the boiling point. Okay. All right. So and let's see here. We've got barium phosphate and we have water. So we have 10.25 grams of barium phosphate, and that's in 50 grams of water. So what we're going to do is we're going to compare the two numbers. That's 10.25 grams and 50.0 grams. Since this is the smaller number and this is the larger number, the barium phosphate is the solute and the water is the solvent. So that's really our definition. Okay, the solution is equal to the solute plus the solvent. The solute is always in the lesser amount, the solvent is always in the greater amount. And the solute in this case is barium phosphate. So barium is a group 2, so that's a +2. Phosphate is a PO4, 3-, that's a polyatomic ion. We're going to take the absolute value of these two numbers, flip the numbers, that's take the bull by the horns, flip and bring it down. So that goes here, this goes here. So it's going to be Ba3, PO4, parentheses, and a 2 out there. And then what we're going to do is we're going to count up the number of cations, that's 3, the number of anions, that is 2. So our Van 't Hoff factor is going to be 3 plus 2, which is 5 for our Van 't Hoff factor. All right. So the Van 't Hoff factor is going to be very important for this problem. And you're always looking for the Van 't Hoff factor for this solute. Okay. So the solute's Van 't Hoff factor, I of 5. That's the number of cations, 3, and the number of anions, 2. Number of cations, 3. Number of anions, 2. All right, fantastic. So we are trying to get the boiling point of this, and then the boiling point of the solvent. What is the normal boiling point of the solvent? The normal boiling point of the solvent is 100 degrees Celsius. This is an exact number. So that means that this has an infinite number of significant figures. So if you want to, you can actually just put a decimal on this there, a decimal here, and then continue with an infinite number of zeros if you want. So, all right. So then what we're going to do is the change in temperature of the boiling point is equal to the constant for the boiling point times I times M. Remember my college girlfriend, what was her name? Kim. I don't know if that's her, or you'll have to figure out, was that her first name or her last name, but it's the constant times the I. The I is for the solute, and then the molality. So what we're going to do is we already have the normal boiling point for the solvent, that's going to be 100. We are given the constant for the boiling point, so we're given this value. We just solved for the Van 't Hoff factor for the solute, and now what we need to do is solve for the molality. So that's our next task at hand. Molality is equal to moles of solute, and in that case, it's the barium phosphate, divided by the kilograms of solvent, and that is the water. The universal solvent, that is water, okay? All right, so what we need to do is we are going to take our 10.25 grams of barium phosphate, convert that into moles. So we're going to go from grams of barium phosphate into moles. Then we're going to take our grams of water and convert that into kilograms of water. We're going to divide those two answers, get our quotient. That quotient is going to be the molality. And then we're going to plug into this equation. We have the constant, that is this number. We have the Van 't Hoff factor, that is this 5. And then we're going to solve for the molality, and then we'll have that one. And then we'll take the product of these three things. That's the constant, the Van 't Hoff factor, the molality, and we will get the change in temperature of the boiling point, and then we will add that to 100, and then we will get our boiling point of our solution. All right, so hopefully that makes sense for you. All right, so now what we're going to do is we are going to, what are we going to do? We are going to take our 10.25 grams of barium phosphate and convert that, that's grams, and we're going to convert that into moles using the molar mass. So what we're going to do is we're going to slide this problem up here so that you are able to see that next part. So we're going to take our 10.25 grams of barium phosphate. That's going to be right here. We're going to convert that to moles, and our 50 grams of water, convert that to kilograms and solve for the molality. So I'm going to slide this up here for just a little bit here, give us some more space. And we're going to take our 10.25 grams of barium phosphate, and we are going to convert that into moles. So 1 mole of the same formula, that's barium phosphate. And remember, what you're going to be doing is you're going to be taking the periodic table, and from that periodic table, you should be able to get all the values of this. And so let me get a periodic table here. All right, so barium, where is barium? Barium is way down here. It has a molar mass of 137.33. Phosphorus, that is right here. That has a molar mass of 30.974. Oxygen, it has a molar mass of 16.00. So we're going to take 3 bariums, 2 phosphorus, and 8 oxygens, sum them up and round that to the fewest number of decimal places, which is 2. The barium has 2, the oxygen has 2, the phosphorus has 3. So we're going to round it to the fewest number of decimal places. So this is going to be 601.94 grams of Ba3, parentheses PO4 with a 2. All right, and then we're going to take this 10.25 times 1 divided by 601.94. This has 4 significant figures. This is an infinite number of significant figures, and this is 5 significant figures. So we're going to round this to 4 significant figures. It's going to be 1.703 times 10 to the negative 2 moles of barium phosphate. All right, so double check that, make sure that you get that same number right there for that. Now what we're going to do is we're going to get our kilograms of water. We have given, the given value here is 50.0 grams of water. And then we're going to convert this into kilograms of water. Pulling out that ruler again finally. Okay, so that we have nice lines. So we're going to take 1,000 grams of water is equal to 1 kilogram. And this has 3 significant figures. This has an infinite and this has an infinite, because both of these are definitions. That's why those are infinite number of significant figures. Okay, and so this is going to equal a 0.0500. So I'm maintaining the number of decimal places, which is 2 here, which is actually 3 significant figures. So I have 1, 2, 3 significant figures. Leading zeros don't count for significant figures. They are important for placeholdership. So that's why those leading zeros are right there. All right, so now what I have is the moles of the solute, and this is the kilograms of the solvent. So what we're going to do in order to determine the molality, so we're going to slide this on up here just a bit, and we still have this equation right here. So I've taken the grams of the solute, converted it into moles. That's right here. I've taken the grams of the solvent, and I've converted it into kilograms, and that's right here. We're going to divide these two and get the molality. So our molality is going to equal 1.703 times 10 to the negative 2 moles of Ba3 PO4 parentheses 2 divided by our 0.0500 kilograms of H2O. And then this will give us our molality. This has 4 significant figures, and like I said before, this has 3 significant figures. So our answer here, rounded correctly, is going to have 3 significant figures. So our molality is going to be 0.341 molal. All right, so now we have all the parts that we need. Now we're going to solve for the change in temperature of the boiling point. Okay, and that is going to equal the constant for the boiling point times the Van 't Hoff factor for the solute times the molality. All right, so let's plug in all those values here at the very top of this sheet of paper, and I'll slide this down so that you can see this. The constant is 0.512 degrees Celsius per molal. The Van 't Hoff factor is 5, and our molality is 0.341 molal. All right, so our change in temperature of the boiling point is equal to 0.512 degrees Celsius per molal times the Van 't Hoff factor, and that's a 5. That has no units, it's a counting number, so it's an infinite number of significant figures, just FYI. Okay, and we'll call this an infinite number of significant figures since it's a constant as well, times the molality, which we just solved for, 0.341 molal, and that number has 3 significant figures. So we're going to have 3 significant figures in our answer here. So we're going to take 0.512 degrees Celsius per molal. Our molalities are going to cancel. We're going to have degrees Celsius. So 0.512 times 5 times 0.341. We're going to round this to 3 significant figures. This is going to be 0.873 degrees Celsius. What are we going to do with this? We are going to go back to our boiling point equation here at the top. So I'm going to slide this up here. All right, so we are going to solve for the boiling point, the normal boiling point, which is 100 degrees Celsius, plus the change in temperature of the boiling point. And so what we're going to do is we're going to plug into that here right now. So sliding this down at the bottom. So our boiling point is going to equal our normal boiling point, 100 degrees Celsius, infinite number of significant figures, plus the change in temperature of the boiling point, that's 0.873 degrees Celsius, okay? And when we add, we use the fewest number of decimal places. In this case, since this is infinite, this has 3 decimal places. I'm going to have 3 decimal places on my answer. So our boiling point is going to equal 100.873 degrees Celsius. And this is our final answer rounded to 3 decimal places. All right. Hopefully that problem worked out really well for you. That was a fantastic problem. And I'm going to zoom out on this so that you make sure that you got all the parts to this entire problem all at once here. So let me zoom out here so you can see the entire problem here. Let's see if we get this all on one section here. There we go. So that's the entire problem. So just as a quick little recap here, we got the boiling point is what we are trying to solve for. We have the normal boiling point of the solvent. That is an exact number since it's not given in the problem. That's 100. And you know that because the normal boiling point of water is 100. Okay, then we're going to add the change in temperature of the boiling point. The change in temperature of the boiling point is equal to the equation Chem. That's the constant times the Van 't Hoff factor times the molality. From these values here given in the problem of 10.25 and 50, they are of the same units. So we're going to figure out which one is the smallest number. The smallest number, 10.25 compared to 50, is the solute. The solute is always in the lesser amount. The solvent is always in the greater amount. So that tells us what our constant is. and our constant is based on the solvent. It also tells you that the solute is going to acquire from the solvent, from the solute, we will acquire our Van't Hoff factor, which is the number of particles in solution, which is the number of cations, 3, the number of anions, 2. We sum them up, we get a Van't Hoff factor of 5 for the solute. That's for the barium phosphate. Now, we also, our exact number of the normal boiling point for water is 100, and that is based on knowing that the solvent is the water, and the solvent is the normal boiling point of the solvent. So what we now have to do, we have the Van't Hoff, we have the constant for the boiling point of the solvent. We have the Van't Hoff factor for the solute. We're going to solve for the molality of the solution, which is moles of solute. That's the barium phosphate divided by the kilograms of solvent. So we solve for the moles of the solute, solve for the kilograms of solvent, divided those two, got a molality. Then we're going to plug that molality into our Kim equation. We got their constant, our Van't Hoff factor, our molality. And then we got a value for the change in temperature of the boiling point. And then we add that to the normal boiling point. And then we get our normal boiling point. Sorry, we get our boiling point of our solution. All right. Let's see here. I am the Crazy Hat Chemist, and you are watching the Crazy Hat Chemist, and we are going to do another problem. We have, I believe, 3 more problems to do. 1, 2, and 3, and we should be able to finish those up really soon. All right, without further ado, let's go on to the next problem, number 17. Here we go. All right, so here is number 17. So let's see if we can get this one up on the road here. And let's zoom in on this so that we've got this whole picture here for us on this problem. All right, so this one here, number 17, says the following. What is the freezing point of a solution containing 38 grams of ammonium nitrate in 150 grams of water? So again, the first thing that we need to do, just like on the last problems, we need to figure out what the solute is and what is the solvent. Okay, and so what we're going to do is we're going to compare this number and this number, okay? And we're going to compare 38 with 150. 38 is less than 150, so the solute is going to be the ammonium nitrate, and the water is going to be the solvent. Okay, and then we need to get the formula for ammonium nitrate. Ammonium is NH4 plus, nitrate is NO3 minus. Both of these are polyatomic ions. Ammonium ion is the only polyatomic cation that I have used in my class, so I'm not sure about you, but we're going to take the absolute value of these two, flip the numbers, bring it down, and we're going to get the formula for ammonium nitrate. Okay, there's the formula for ammonium nitrate. We know that that is the solute. So we need to calculate the Van't Hoff factor for ammonium nitrate, which is the number of cations, that's 1, the number of anions, that's 1. So it's 1 plus 1, that's going to equal 2. So the Van't Hoff factor for ammonium nitrate is 2. All right, so now what we're going to do is the freezing point equation is equal to the normal freezing point of the solvent plus the change in, minus the change in temperature of the freezing point. So the normal freezing point of the solvent and the normal freezing point of water is 0 degrees Celsius, and this is going to be an exact number, okay? So what we have to do is we have to calculate the change in temperature of the freezing point. And what is that equal to? Change in temperature of the freezing point, that's equal to the constant of the freezing point for the solvent times the Van't Hoff factor for the solute times the molality of the solution. So that's what we're going to solve for right now. Since we already have the 0, the normal freezing point, and we're going to subtract this product, we're going to subtract the change in temperature of the freezing point. That product is going to be the constant for the freezing point times the Van't Hoff factor times the molality. Well, we already have the constant, so we already have that. And we just solved for the Van't-Hoff factor. We already have that. That is 2. So now what we need to do is solve for the molality. So that is our next step right here now. All right, so again, what we're going to do is we're going to solve for the molality. And molality is equal to moles of solute, which is ammonium nitrate in this case, divided by the kilograms of the solvent, which is the water in this case. All right, so we're going to do each of these individually and then cram them back into there, and then we will have all our parts. So this is the constant for the freezing point. The Van't Hoff factor is a 2. That goes right there. That's an infinite number of significant figures without units on it. It's just counting. That's why it's infinite. And then we're going to solve for the molality right here, and that's going to go right there. All right, so the first thing we're going to do is we're going to solve for the moles of the solute. And so I'm going to slide this on up. You should see that we have 38 grams of solute. And then we're going to solve for the kilograms of solvent. That's 150 with a decimal grams of water. So I'm going to slide this up here a little bit so that we have a little bit more space to solve for the molality. And so we have 38 grams of ammonium nitrate. And let's solve for the moles of ammonium nitrate. Here we go. All right, so what we need to do is we're going to need to get our periodic table. We're going to find hydrogen, and that is its molar mass is 1.0079. We're going to find nitrogen. Its molar mass is 14.007, and oxygen, and its molar mass is 16.00. Hydrogen has 4 decimal places on my periodic table. Nitrogen has 3, and oxygen has 2. So the fewest number of decimal places is 2, and that's what we're going to round our molar mass to. And so that will be 2 decimal places. So that will be 80.05 grams of ammonium nitrate, NH4NO3. That's equal to 1 mole of NH4NO3. And so what we're going to do is we're going to look at the number of significant figures. This is 2 significant figures. This is an infinite number of significant figures. This is 4 significant figures. We're going to take 38 times 1 divided by 80.05 and round that to 2 significant figures. That will be 0.47 moles of ammonium nitrate. So that's going to be my numerator term in my molality. Now I'm going to get my denominator term in my molality. And if you recall from up at the top, it was 150 with a decimal grams of water. And I need to convert this into kilograms of water. And this is really simple. 1,000 grams, 1 kilogram. And this has 3 significant figures because that decimal lets us know that trailing zeros count. As this is an infinite, this is an infinite because this is a definition right here. And then we're going to take 150 times 1 divided by 1,000. And we're going to get 0.150 kilograms. All right, and effectively what we're going to do is we're going to take this number in the numerator, this number in the denominator, and we're going to divide. And that will give us a molality. But we're going to slide this up, and I'm going to do that here for you. Actually, we're going to do it right here because we already have this kind of set up here. So here we go. I'm going to put it right there. 0.47 moles of ammonium nitrate divided by 0.150 kilograms of H2O. Okay, and the number of significant figures, leading zeros don't count. This has 2 significant figures. This has 3 significant figures because trailing zeros count with the decimal, leading zeros do not count. So our molality here is going to be 3.1 molal. So we're taking the 0.47 divided by 0.150, and we get 3.1 molal. All right, now what we're going to do is we're going to calculate our change in temperature of our freezing point. So I'm going to slide this up here just a little bit. So change in temperature of the freezing point, that's equal to K times I times M. At the very top of this here, we had the constant for the freezing point, that's 1.86 degrees Celsius per molal. And the Van 't Hoff factor that we calculated for the solute, which was ammonium nitrate, was 2. Again, that's a counting number. It's an infinite number of significant figures without units. And we just solved for the molality. That is 3.1 molar. Okay. What we are looking here at, we're going to say infinite number of significant figures, infinite, because that's counting. That's a definition. This is counting, and this is 2. Whoops. Let's see if we can write numbers and speak them at the same time. So that's 2 significant figures. So we're going to take 1.86 times 2 times 3.1 molal. The molalities cancel out, amount of degrees Celsius. This is going to be 12 degrees Celsius. All right. So now what we're going to do is we're going to plug this into our freezing point equation. Okay. And what I'm going to do is I'm going to slide this on up here at the top here because we had already written down our freezing point equation earlier. So I'm just going to write this down right here. So we have the freezing point is equal to the normal freezing point, which is 0. That's an exact number, minus 12 degrees Celsius. And so we're going to take 0 minus 12, and then we're going to get negative 12 degrees Celsius. And that is going to be our freezing point, negative 12 degrees Celsius. That's it. So what I'm going to do is I'm going to zoom on out here so that you can get this whole picture of this entire problem, so you can see all of that, and then just do a real quick summary recap of the whole entire thing. So what we want to do is we want to calculate the freezing point of this solution. So we first need to figure out what is the solute and what is the solvent. The solute and the solvent are based on the amount that you have, and you have 38 grams of ammonium nitrate. That's a smaller number compared to the 150 grams of water. So therefore, the ammonium nitrate is the solute, and the water is the solvent. The constant is based on the solvent. Okay, so that's why the constant is based on that right there. And the solute, I'm going to obtain the Van 't Hoff factor. So I need to get the formula for ammonium nitrate. It's NH4, 1 plus, and NO3, 1 minus. And that is the ammonium ion and the nitrate ion. And that's 1 ammonium ion, 1 nitrate ion, and that's a Van 't Hoff factor of 2. So now I have the constant. I have the Van 't Hoff factor. I'm going to solve for the molality. I'm going to get the moles of the solute, 0.47, the kilograms of solvent, 0.150 kilograms. Divide these two numbers and get the molality of the solution. And then I'm going to get the change in temperature of the solution, which is the constant times the Van 't Hoff factor times the molality of the solution. So the constant of the solvent, 1.86 degrees Celsius per molal, times the Van 't Hoff factor of the solute, that's 2, times the molality of the solution, 3.1 molal, and you get 12 degrees Celsius. And then we come back over here and we plug into our freezing point equation, which is the freezing point is equal to the normal freezing point. That value of the normal freezing point is an exact number based on the solvent. The solvent is water. The normal freezing point for water is 0. And then we put in our change in temperature of the freezing point, and that's 12. And we do a little subtraction there, and we get negative 12 degrees Celsius. So, perfect. All right, so we're going to slide this one away, and then we are going to do the next problem, and that is problem number 18. But before we do, remember, I am the Crazy Hat Chemist, and you are watching me here on YouTube. So please subscribe to my YouTube channel. I would greatly appreciate that, and help out me think that I'm actually touching and encouraging you to enjoy and get better with your chemistry. So here we go. We're going to do our next problem here, and it says, what is the pressure of a gas when the solubility is 0.35 grams per liter, and the pressure was 1.5 atmospheres and a solubility of 1.2 grams per liter? This is a Henry's Law problem, just like we did a Henry's Law problem before. So this is actually a Henry's Law problem. Henry's Law. And what is Henry's Law? Solubility of X over pressure of X is equal to solubility of Y over pressure of Y. All right, so that's what we're doing there. We're plugging into the Henry's law equation. And so how we apply this here is we have this value. This is a solubility. And we're trying to find, it says, what is the pressure of that? So 0.35 grams per liter over the pressure of that gas, we're going to solve for that, is equal to the 1.5 atmospheres, and the pressure, sorry, the solubility is 1.2 grams per liter. All right, so this is a very simple problem. Crisscross applesauce. I have two significant figures everywhere on this problem. So when we do the math in our calculator, it's 0.35 times 1.5 divided by 1.2. Remember, it's crisscross applesauce. We're solving for the pressure of the gas. So 0.35 times 1.5 divided by 1.2. I'm going to have two significant figures on this problem, and I'm going to get the pressure of the gas, and that will be equal to 0.44, and the units will be atmospheres. That's it. It's that simple. Oh my gosh, no way. All right. Now we have the final last problem here. And so here we go. It says, what has the highest boiling point of these three things? So we have 0.25 molal potassium chloride, 0.35 molal sodium chloride, or 0.24 molal barium chloride. All right, so in order to do this problem here, we need to figure out what is the deal here. So we're looking for the highest boiling point. So we're going to go for this equation here. The boiling point is equal to the normal boiling point plus the change in temperature of the boiling point. Okay, so what we're going to do is a comparison of all three of these. I'm going to slide this on up so that we're just focused on this one problem here. So it doesn't matter what this is in. So what is the solvent? I don't know what the solvent is, but let's just come up with that the solvent is the same for all three. That would be the concept here that you're looking for, is that the solvent is the same for all three of these. And we'll just take water. So we'll just say that the solvent for all three is water. Therefore, the normal boiling point for the solvent is 100. And then, since all of these are in the same thing, we're going to figure out what the change in temperature of the boiling point, what this means. It's the constant for the boiling point times the Van Hoff factor times the molality. Okay. And so hopefully you understand the highest boiling point is the one with the largest change in temperature of the boiling point. So the largest change in temperature when added to 100 will give me my largest boiling point. Okay. If I was looking for the lowest boiling point, I would be looking for the smallest change in temperature. So since I'm looking for the highest boiling point, I'm looking for the largest change in temperature, which means that I'm looking for the largest Kim. So I'm going to compare the Kim of all three of these solutions. That's what I'm looking for. So the change in temperature of the boiling point is equal to Kim. Change in temperature of the boiling point is equal to Kim. Change in temperature of the boiling point is equal to Kim. Okay, and so I'm going to plug into this equation. And whichever one is the largest will give me my largest change in temperature of the boiling point. When added to the normal boiling point would be the highest. So I'm looking for the largest change in temperature, which would be the largest Kim. So since they are all in the same solvent, we'll have to assume that. That means that the constant for all three is going to be the same, because the constant is based on the solvent and not the solute. All right, now having done that, now we need to figure out what is the Van Hoff factor for each one. So the Van Hoff factor for potassium chloride is there's one potassium, one chloride, so that's a Van Hoff factor of 2. Van Hoff factor for sodium chloride. There's one sodium, one chloride. That's a Van Hoff factor of 2. What's the Van Hoff factor for barium chloride? There is one barium and 2 chlorides. That's 1 plus 2. That's a Van Hoff factor of 3. All right. And then we are given the molalities of each one, and I'll plug that in, 0.25 molal and 0.35 molal. And 0.24 molal. Okay, and so what we're going to do is we're going to get the product of these two, get the product of these two, get the product of these two, and we're going to compare those values. So that is 0.50, and this is for the KCl, just so that you understand. 2 times 0.35 is 0.70. That's for the NaCl. And then 3 times 0.24, that's equal to 0.72 BaCl2. And so which of these three numbers is the largest? That is this one. So therefore, this one will give us our largest Kim, which will give us our largest change in temperature of the boiling point, which will give us ultimately our largest boiling point. So which of these three has the highest boiling point? This one right here. And then we're going to answer one more question here, just to throw this in here. Not that I'm asking this question, but you might be asked this question on an assessment of some kind. Which one has the lowest boiling point of all these three? That would be this one, lowest. So the lowest boiling point is based on the smallest change in temperature of the boiling point. So, perfect. Let me answer one other question here. And which one has the lowest freezing point? So the freezing point equation is equal to the normal freezing point minus the change in temperature of the freezing point. Again, if we assume that they're all in the same solvent, which they are, then which one would have the lowest freezing point? Well, the lowest freezing point would be the largest Kim, which would be the largest change in temperature of the freezing point. This one would have the lowest freezing point would be the barium chloride. Hopefully that makes sense. Okay. The lowest freezing point would be the barium chloride because this has the largest Kim and that will be the smallest value. All right. Lowest freezing point, which the barium chloride, which would have the highest freezing point. That would be this one here with the potassium chloride because it's the smallest value, the highest freezing point. All right, so I've answered not only the question that was at hand on this problem, but I've answered 3 other questions as well. So hopefully you followed that. I am the Crazy Hat Chemist, and please subscribe. Give me a thumbs up. Here's a thumb. There's a thumb. Give it up. Put it up. Put it up. Put it up. Put it up. 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 And please subscribe to my YouTube channel. And I love you a lot. And we'll see you next time for more Crazy Hat videos. All right. Talk to you later. Bye for now.